All right, guys, we're going to continue our instruction on acids and bases. You guys remember the last video lesson we learned about the pH scale. Remember, we can use the pH scale for various solutions, and a pH reading of a value less than 7 would indicate that the solution is acidic, and a pH value greater than 7 would indicate that the solution is basic. Remember, we said quite simply that what makes bases is the presence of the H plus ion. You guys remember that? And what makes bases is the presence of the OH minus ion. Now we're going to clarify that a little bit more here today. Well, then there's a further distinction when it comes to acids and bases. We can have what are called strong and weak acids and bases. So, for example, here are two acids. I know this looks, this one you guys should recognize as an acid. You guys remember from nomenclature, you recognize an acid has a hydrogen on front. This is hydrochloric acid. This actually is acetic acid. I know you're looking, you're like, well, where's the hydrogen in front? Sometimes it can be written in a different way. Like in this case, we could just put, this is a hydrogen that actually is given up. And so we could actually put a hydrogen and then we could write it as, so sometimes it's written like that just so you guys see it's the same amount of atoms. So the hydrogen's on front so you can recognize it as an acid. But the reason why it's written like that is because this hydrogen is actually attached to an oxygen, so sometimes it's written like that. But nonetheless, so you guys see what happens is these are both acids, and so what do acids do? They donate hydrogen ions. So this hydrochloric acid, and the way you guys could look at it is you can look at it dissociating. So hydrogen chloride will dissociate into hydrogen ions and chloride ions. Once again, the presence of those hydrogen ions is really what makes hydrochloric acid an acid. In the same way, acetic acid, which is just another word for, you guys, your vinegar that you would put, in food at home, is a dilute acetic acid solution. So in like fashion, you see what's happening is the hydrogen, you could look at it from here, the hydrogen from the acetic acid is dissociating from the rest of the substance, and you have H plus and you have what's called the acetate ion. Once again, you guys see it's the presence of the H plus ion is really what makes these two acids acids. One thing you'll notice though is, you'll notice this has just a right arrow, and you guys remember this has a reversible arrow. Remember we learned that in the equilibrium unit. When you have just a right arrow, what that's indicating is this reaction goes to goes to completion, meaning all of your hydrochloric acid will completely dissociate into these respective ions. The difference in this, by the way, is what we call a strong acid. Strong acids, and you guys could put this, completely dissociate. That means break apart. Dissociate. Completely dissociate. This, you'll notice with the double arrow, what that's indicating is some of it dissociates into these ions, but then the ions also have an attraction for each other and reassociate back into the original acid. So what we would say here, this would be an example of what's called a weak acid. And weak acids only partially dissociate. And so what you would have is, so if you put this acetic acid in water, you're only going to have a very little of it's going to break up into the H plus and the CH3O minus ions. So you guys, this would help explain why you might expect a strong acid like hydrochloric acid to be more dangerous than a weak acid, acetic acid, because once again, what is it that makes acids so reactive? It's the presence of these H plus ions. Well, if strong acids completely dissociate, then you might expect with equal concentrations of these, more H plus ions with a strong acid than you would have with a weak acid, which only partially dissociates. Okay, so let's look a little bit more at this. Before that, Cobb says, maybe I shouldn't have motioned that speeder to pull over. Okay, so here, you guys, these are water molecules.
I understand the differences between strong and weak acids, but why does the hydrogen ion combine with water? Let's look at the particle view of HCl in water again.
You guys see, this was HCl, and you notice the hydrogen ion dissociated from the chloride ion. So look what's happening. You put it in water.
A hydrogen atom has one proton and one electron. The hydrogen ion is simply a proton.
Okay, so you guys will be noticing something here. that we'll bring up here. Look at this.
A proton doesn't exist in an aqueous solution. It attaches to one of the lone electron pairs on the oxygen atom.
Then the correct equation for the ionization of HCl would be hydrochloric acid plus water yields chloride ions and hydronium ions.
So, you guys, this should actually, even though we tend to write it like this, which is really simplistic, in actuality, here's really what's happening. So we have hydrochloric acid. You're going to put hydrogen chloride in water. So you guys, once again, what makes it an acid is the fact that it donates a hydrogen ion. So you guys remember there's lone pairs of electrons on the oxygen in water. So what that'll do is it will attract a hydrogen ion from that. And so then what happens is, so now the hydrogen attaches actually to water. So in actuality, we don't have H plus ions floating around in water. It's much too reactive. Those H plus ions will actually attach to water molecules and form this, H3O plus. So you guys see, it pretty much, it's the exact same thing going on, but sometimes for simplicity's sake, we just write H plus rather than H3O plus. But whenever you guys see H plus, think in actuality, that hydrogen ion is actually attached to a water molecule and H3O plus. This also, by the way, is called the hydronium ion. So you guys, whenever you hear me talk about H plus, in reality it's a hydronium ion. And you guys, in the same way, I can do this with the acetic acid. I can just write it more properly as the acetic acid reacting with water. You guys notice in the simplistic form, we just don't show the water because it's typically in an aqueous solution. Remember, it's a reversible reaction because this side of the reaction is actually, the reactant side is actually favored. But anyways, nonetheless, what makes it an acid? It donates a hydrogen ion to water. And so we get H3O plus, and then we have CH3COO minus. But you'll notice it looks very similar to this. Sometimes for simplicity's sake, we just write it very simply with the H plus, but in actuality, it's H3O plus. So some of our employees now work from home. We'd like to try something similar with you. The working from home part? No, the not working here part. Okay. Okay, here we go, guys. Here's hydrochloric acid.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution.
So once again, guys, hydrochloric acid is a strong acid, and what does that mean? It means it completely dissociates. Notice all the hydrogen chloride separated, and therefore you can expect a higher concentration of H plus ions, which is really what is the reactive component of an acid, which explains why acids typically can be reactive, especially if they are strong acids. Now look at a weak acid.
Hydrofluoric acid is a weak acid because it only partially ionizes. At any one moment, most of the HF molecules have not split into their ions.
So once again, hydrofluoric acid is what's called a weak acid. You'll notice at any given time, didn't you see that most of the hydrogen and the fluorine stays associated together? There's a strong attraction between these. They're reluctant to dissociate. But occasionally some will dissociate, but so at any given time, right? You guys saw that? You might have a few ions that are dissociated. But in general, with your weak acids like acetic acid, hydrofluoric acid, the left side of the reaction is favored where they stay in the associated form, okay? And so for that reason, you guys can see at any given time, the hydrogen ion concentration is relatively low, which would help explain why weak acids typically are not as dangerous as strong acids, assuming you have the same concentration, okay? So you guys, if you were to get the pH, let's say we had a 3 molar solution of hydrochloric acid and 3 molar solution of acetic acid. Notice it's the same concentration. Remember that also impacts the pH. Would we expect the pH of 3 molar hydrochloric acid to be the same as the pH of a 3 molar acetic acid solution? The answer is no. In fact, if you were to measure the pH of the solution, you would find that the pH of this solution is much lower. You guys remember the lower the pH? You guys remember on a scale of 1 to 14, the lower the pH, the more acidic? This would have a lower pH value than this, and why is that? It completely dissociates. Remember, when you're measuring the pH, you're essentially measuring the hydrogen ion concentration. Therefore, if the hydrogen ion concentration is larger, that's going to indicate it's more acidic and reflected by a lower pH value. And likewise, this will have less hydrogen ions, once again, because only a few dissociate, and therefore it's going to be less acidic and it's going to have a higher pH value.
NaOH, sodium hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
You guys remember we were talking about acids and bases. You remember what we were saying makes bases bases? It's the hydroxide ion. Remember we were saying these are just as reactive as the H plus ions, which are in actuality hydronium ions. So in like fashion, what would be an example of a strong base? That would be a base that completely dissociates, and therefore you're going to have a larger concentration of these hydroxide ions, which is what makes the base the base. Okay, I think I want to introduce something else to you. So you guys will notice with this, you guys remember with reversible reactions. You guys, and you remember we said that this goes to completion. So that's why I write one arrow. But you know what you could do? You could just write it like this, and you're showing this arrow is very, the larger arrow is pointing to the right, indicating the forward reaction occurs much faster, and therefore than the reversible reaction. But you guys remember with any, so you could kind of look at it as a reversible reaction. Here's the point, guys. You guys remember with a reversible reaction, you can always write what's called an equilibrium expression. You guys remember how to write the equilibrium expression? Remember the equilibrium expression, so something equals a constant. You guys remember from our equilibrium unit. So what equals a constant? You guys remember it's the ratio of the products to the reactants. So then I would say the K value. You guys, in fact, you know what? I'm going to use the easier equation. Like I said, this is the more accurate. But a lot of times when we're talking about acids, we just call it H plus. We don't want to write H3O plus, but we know it is actually attached to water molecules. So if I was to write the equilibrium expression for this, I do the concentration of my products, right? You notice it's only raised, it's not raised to a power because the coefficient's a 1, times the concentration of the chloride ion, all over. And you guys remember, even if I was to do this, you remember I wouldn't include water. You guys remember in your equilibrium expression, you never include pure liquids or pure solids. You only include aqueous or gases. So it's the concentration of the products over the concentration of the reactant. And you guys see that would be the equilibrium expression. You know what? We give it a special designation, this K value. We give it a special designation, we call it Ka. And why would we call it Ka? For obvious reason. What do you guys think? It's the equilibrium constant for an acid, so it's the Ka value. Okay? And you guys, if we were to do it likewise for this reaction, right, with the weak acid, once again, I'm going to choose the easier, the more simpler one to write. So I'm going to call it, once again, I'm going to call it Ka because it is for an acid, so it's the equilibrium constant for an acid. Once again, it's the concentration of the products. So concentration H plus ion times the concentration of my acetate ion all over the concentration of my original acid. So now the question is, if we were to compare these two, what would we find, guys? Once again, this is a strong acid, this is a weak acid. What's meant by a strong acid? Completely dissociates. So what would you guys expect? You would expect the concentration of your ions here on the product side, you guys see it's in the numerator, to be much greater than that on the reactant side. So the numerator is very large and the denominator is very small, essentially 0. So what kind of value are you going to get? What kind of Ka value you're going to get for a strong acid? You're going to get a value that's much greater than 1. Basically what I'm saying is a very, very large number. Compare that with the Ka value for a weak acid. You guys remember with the weak acid, you remember I was saying in the reversible reaction, the reactant side's favored. There's actually a strong attraction between this acetate ion and the hydrogen ion, pretty much stays intact. So therefore, very little of it is going to dissociate. So the concentrations of my product, which are in the numerator, are going to be very small. So I'm going to have a relatively small number in my numerator, divided by a relatively large number, right? Because most of it stays intact, so the concentration of the reactants is going to be greater than the product. And therefore, if I have a small number divided by a large number, what could you guys predict about the Ka value? When you guys expect it to be much less than 1. You're having a small number divided by a large number. And in fact, if we look, guys, I could give you a Ka chart, which just is a list of the various Ka values at a particular temperature. And what you'll notice here is, so once again, look, these are just various acids. You guys see how the easiest way to look at it is? It's just most of them start with a hydrogen. You guys remember look at acetic acid. See, that's one of the exceptions. Sometimes I'll put the hydrogen here, which is reflective of which atom it's bound to in the actual chemical structure. But for the most part, you would identify these all as acids. And you see what makes them acids? They all, to some measure, dissociate and form H+ ions. You guys see that? That's all similar. Now, how do they differ? They differ by Ka values. Now, look at the top 6 or 7 here. Notice we don't even give a value. We just say it's very large. What are we saying? How can we identify those acids? Perchloric, hydroiodic, hydrobromic, hydrochloric, nitric, and sulfuric acid. Those are strong acids for the most part, guys. They completely dissociate. So the concentration of your ions, your dissociated ions, is so much greater than that of your original acid that, for all practical purposes, the Ka, we don't even put a value. We just say it's very large. Essentially, what are we saying? It goes to completion. That's why we'll typically write strong acids with a single arrow pointing to the right. Compare that with all these other acids. All these other acids have values. Now, how would you guys describe these Ka values? Look at 10 to the negative 2, and then it gets smaller and smaller. These are all very small Ka values. What does that indicate about these acids? They're all weak acids. They only partially dissociate, and therefore your Ka value, once again, small number divided by large number, is going to be very small. So you can tell the strength of your acid via the Ka value. The larger the Ka value, what does that indicate? The stronger your acid. What does stronger acid mean? It means it completely dissociates, and you're going to have a high H+ ion concentration. The lower the acid, and you guys, this is kind of interesting. Check this out. Look at the last one. I know it kind of cut off there, but that's water. You can actually consider water a very weak acid. Why? Because water, and we're going to show you guys that, can actually dissociate and form H+ ions. But you'll notice, look at the K value for water. It's the lowest of all of them. It would be your weakest acid. Okay, so once again, from the Ka values, you can tell how strong or how weak an acid is. It says, I caught you doing 30 miles below the limit. Oops, I'm sorry. How about if I just speed up on my way home, kind of average it out? Okay, now look at the practical difference between these. Hydrochloric acid, acetic acid. See if it goes. Oh, that's not good. Well, you know what? I don't know if the video is working on this, but basically, you guys, right? We've done this before. We could take a light bulb, and you guys, in order for a light bulb to light up, you obviously need a power source, right? So this would be plugged into a power source, but nonetheless, you would also need, you guys, these have 2 electrodes here. You'd also need the flow of electrons. You guys remember, for that, you need a complete circuit. So the electrons that build up here have to be able to have a way to get from the negative terminal to the positive terminal, and it's the movement of those electrons that provides the energy to light the light bulb up. Well, you can put it in like a solution like hydrochloric acid, and it will light up. Guys, what is facilitating the movement of the electrons from one electrode to the other? What's completing the circuit? You guys remember from first semester, it's the presence of ions. What'll happen is, right, think about electrons coming here. Wouldn't positive ions be attracted to the negative electrons? And then, so the positive ions will pick up electrons and then become neutral. Those would proceed to be able to move through the aqueous solution to the other electrode and then give up that the electron that they picked up from the negative terminal, and thus deliver it to the positive terminal. And so the ions serve as a transport system for those electrons to continue to flow. And you'll notice it's lit up brightly. What if we took a light bulb and put it in acetic acid solution? Think about, what would you guys anticipate if we put it in an acetic acid solution that has the same concentration? Now you notice this is lit up, I don't know if you noticed, but it's lit up brightly. If we put a light bulb in the acetic acid solution, would there be a difference? Here's what you might expect. And I know it's kind of hard to see. The light bulb will light up, and why will it light up? because there is the presence of ions. But hopefully you guys will notice, look, it's lit up more dimly than that of the hydrochloric acid. And what would explain that? When you guys agree, there's simply less ions. So there's less ions in the solution that facilitates the transport of the electrons, and therefore you're going to have less electricity flowing through that light bulb, and therefore it's not going to light as brightly. And what would explain that, guys? Acetic acid is a weak acid. Remember, most of it prefers to stay intact, holding on to the hydrogen ion. Therefore, the ion concentration is lower. Therefore, it is less conductive. I don't know what's going on with my videos. Let me try it again, guys. Yeah, it's still not working. Let me have to kind of show what's going on here. So, you know, this was going to show on a molecular level what's happening. So I guess we won't show that. But then, anyways, this is representing the acetic acid molecules. You guys see that the large part of the molecule is this part, and then the little blue ones representing the H plus. So if we were to see this, if the video would work, you guys would see only a few of them dissociate. Remember, and it's actually dynamic. It dissociates and then can come back together, but at any given time, you're only going to have a small percentage of these acetic acid molecules dissociated, as is expected with a weak acid. All right, guys, so hopefully you guys have a better understanding of what's the difference between some acids based on if it's strong or weak. It has to do with if it dissociates completely or partially, and then we can get a numeric measure of how acidic or strong or weak an acid is via the Ka value. Oh, one last thing. That's right. So, you guys, here I would show you guys this. I'd show you some water, and I'd ask you, okay, what's in the water? You'd say, well, duh, Mr. Wilson, water molecules, H2O molecules. And I'd say, yep, you know, for the most part, you're right, but there is actually other things in this, and it doesn't have to be polluted water. Let's say it's pure water, right? So it's not like pond water or something like that, or polluted water. There is a small measure of something else in here. What actually happens in water is what this is showing. You guys, in fact, it would be good if you guys copied this down. So think about water molecules, and think about water molecules are randomly moving. And what are water molecules doing? They're colliding. Well, occasionally what will happen is water molecules will collide, and a hydrogen ion from one of the water molecules will attach to one of the lone pairs of electrons on the oxygen of an adjacent water molecule. And so you see what happens if it donates a hydrogen ion. Now, once again, we have an H3O plus. You guys remember we recognize that from an acid. And then with the water molecule that donated a hydrogen ion, what's left? A hydroxide ion. So, you guys, in solution, in fact, you guys, how we'd write that down, we'll just, so this is what I want you guys to do, is show that this is actually what's happening. Oh, you know what we would call this? Well, here, I'll give it a title. So think about water molecules colliding. Notice it's a reversible reaction. And water molecule can donate a hydrogen ion to the other, creating H3O plus, and what's remained is an OH minus. It's a reversible reaction. This is called the auto. You guys remember auto means it does it on its own. Auto ionization. It's called ionization because then you're forming ions of water. This is the auto ionization of water. Now it's a reversible reaction. Now you guys think about it. What side of the reversible reaction do you guys think is heavily favored? You guys, without a doubt, what do you guys think the majority of the stuff in here is? You guys, it's just water molecules. Most of them are just staying as water molecules. But once again, occasionally, water molecules will collide in such a way that hydrogen will transfer from one to the other. So, when you do, like you could do a K expression for this. I don't want to confuse the issue, but you would imagine the K value for this would be a very small number. You guys remember when we saw water on that Ka chart? It had the lowest value because the concentration of these is very minimal. The thing I really want to communicate to you guys is, in any kind of aqueous solution, water-based solution, this reaction is happening. So in any water-based solution, you primarily have water, but you also have H3O plus ions and OH minus ions. So what that means is, you guys, when we're talking acids and bases, it's typically in an aqueous solution, it's in water. So what that means is, even in acids, not only do you have H3O plus ions, but you also have OH minus ions. Why? Simply due to the autoionization of the water molecules that make up that solution. So you guys, I wasn't entirely truthful with you when I said what makes acids acids. You guys remember what we were saying before? We said what makes acids acids? We said H plus ions. Which you guys remember, H plus ions, same thing as H3O plus ions. And you remember what I said? What makes bases bases? I said OH minus ions. But the reality is, guys, even in acids, you're going to have H3O plus ions and hydroxide ions, once again, due to the autoionization of water. And in bases, you're going to have not only hydroxide ions, but you're also going to have H3O plus ions, once again, due to the autoionization of water. So in reality, you guys, what makes acids acids? Oh, you guys think about this. If this is pure water, what do you guys think you could say about the concentration of H3O plus ions and the hydroxide ions? Notice, look, for every one of this that reacts with this, I form one of this and one of this. In pure water, guys, but this is the case. You guys know pure water, you guys remember it has a pH of 7. We would say it's neutral. So in a neutral solution, what is it that makes it neutral? It's neither acidic or basic. What do you think you could say about these concentrations? Isn't it the H3O plus concentration is equal to the hydroxide ion concentration? That's what we mean when we say it's neutral. So you guys, what is it that makes an acid an acid? And you know what? I'll use H3O plus this time. Really, what makes acid an acid, I won't put this anymore. What makes acid an acid is when the H3O plus concentration, what do you guys think? Compare it, is greater than the hydroxide ion concentration. That's what makes an acid an acid. See, at this point, the pH of this, in this situation, the pH would be 7. When you have this situation, when the H3O plus concentration is greater than the hydroxide ion concentration, you have the pH, here we should put pH. pH is less than 7. And so you guys, what is it that makes a base a base? Not just the fact that it has hydroxide ions, because once again, hydroxide ions are in any water-based solution. It's when the hydroxide ion concentration is greater than the hydronium ion concentration. I see it's the opposite. And in that case, when you get the pH value of that solution, you're going to get a pH value greater than 7. So once again, I wanted to clarify that. What makes an acid an acid? The hydronium ion concentration is greater than hydroxide. What makes a base a base? The hydroxide ion concentration is greater than hydronium ion concentration. All right, guys, that's all I got for you. Until next time.